Right, well, welcome everybody to the May 2026 meeting of the Mornington Peninsula Astronomical Society. My name's Peter, and as usual, I'll just go through some of the things that have popped up in the last month, some of them weird and wacky. Yeah, that's right. The Pentagon has kindly released more UFO files, which I have to say I'm totally underwhelmed by by what they put online. So you'll see in the video at the top left there pictures of what looks suspiciously like a drone to me, and its movement across the sky. And of course it's heavily redacted, so there must be someone's name written all over that screen to have all the black bars all over it. And some of these things you just can't tell the scale at all because there's nothing for comparison, so absolutely hopeless. Down to the bottom right hand side with the green and the funny gold disc there, that of course is an impression that I think one Ben said tonight looks like something from a 1980s video game, and I'd say I totally agree with that, or AI generated at the best, and I'm not convinced in the slightest by that thing. And then they also released some images from Apollo 12 and even Apollo 17 taken on the moon. And there's one picture shown at the middle left on the surface of the moon. And you can see the shadow of the astronaut that took the picture, sort of extending across the image. And then they've highlighted tiny little fragments of what's in the sky. Now, I don't know whether they checked what stars were actually there for a start, or any bits of junk that happened to be floating by, but this, of course, is in the era of photographic film. This is not digital cameras. They didn't use digital cameras. So they could also be artefacts due to cosmic rays and indeed particles of the solar wind actually altering the film. Now the thing that really bothers me actually about that photograph is if you notice the middle of the horizon there, it looks all a bit fuzzy. And you shouldn't have any fuzziness on the moon because there's no mist there, no moisture, no atmosphere to actually cause things like halos and glories to occur. And so what that suggests to me is that a lot of these you're actually looking at internal reflections within the optics of the system myself. So I don't know whether you notice that there.
I think some of those UFOs in the sky also appear in the shadows on the ground.
Ah, wow. Oh. But was the flag waving?
No, there's little blue specks and things like that in the shadows.
In the shadows as well. Oh, I'm convinced, yeah. Over in the top right-hand side, a bit of a surprise. You can see on the little chart, the little graph shown on the top right, you see Earth on the left and the moon is over on the right. And they've actually worked out a cheaper and more fuel-efficient way to get to the moon than just going straight there. So the way that Artemis, for example, or Apollo did to go straight from the Earth into lunar orbit wasted 1.76% of the fuel. They found a method by looking at 30 million different approaches to go from the Earth to the moon, and the optimal one was the one that is drawn there. You see it sort of curls upwards from the Earth, flips in front of the moon, and goes into orbit around the Earth and Moon Lagrange point. Now this is a point in space where gravity essentially cancels out. And so what they say is you first of all send your craft to go to the Lagrange point. So you zip by the moon, go to the Lagrange point, you can park it there. So you might have like a transfer hub of something there, much like in, say, 2001 A Space Odyssey. And then when you want to go to the moon, you can flip out of that Lagrange point and then go into the moon. And in the process, overall, you've saved 1.76% of the fuel, which is considered to be a fortune, particularly if you're throwing a lot of rockets into space, trying to build a base on the moon, for example. So that one was only published a couple of weeks ago. That they came up with that, a Portuguese research team. Down the bottom left-hand side, we see NASA's Near-Earth Object Surveyor, which is under construction at the moment, and that's due for launching in September next year. And this is one that is going to search for potentially Earth-striking asteroids and comets, and it's going to be sent out to, in fact, the Lagrange point of Sun and Earth, which is different from the Lagrange point between Earth and Moon. This is the one between the Earth and the Sun. And it's not looking for them in the usual way. It's an infrared telescope, so it's going to be tuned to actually look for the infrared signature of them, given the temperature of them, and not looking at reflected sunlight from the sun. So it's a different approach, and they believe that they're going to pick up a lot more of these hazardous near-Earth asteroids, all as part of planetary defence, apparently. And finally, on the bottom right-hand side there, University of New South Wales team has found another 27 exoplanets that are actually around binary stars. So this is pretty much like in Star Wars, the solar system Tatooine that had two suns. This is the same sort of thing, and the planets go around the two suns. So this is part of like a three-body problem. And so they've put forward 27 exoplanets, which are yet to be confirmed by someone else. Right, so tonight, welcome everybody. New members since we last met. We've had Lucinda Shepherd, Vanessa Richards and John Vrazovs here. Anybody here tonight of those? No new members here tonight. Good, we'll move on. So we welcome them to the Society. As usual, I'll look at the events over the past month and coming up, and then I'll throw over to Chris for his monthly photo challenge. Sky for the month will be given by Guido remotely, so he's dialing in from the UK for that one. Then we'll look at neutrinos and the universe and everything. This was given by a neutrino expert, well and truly a neutrino expert, Associate Professor Kirsty Duffy. And then we'll look at Are There Extra Dimemsions, about a 10-minute one from Michio Kaku. And then we'll close looking at aerosols and smoke and that around the Earth. And it's quite revealing. So, recent events. On the 18th of April, which was just after the last meeting, we had a Working Bee and Members barbecue. And Paul Albers kindly did a repeat performance of his defibrillation talk for members here on the Members' Night. That following Wednesday, or in fact Thursday, we had a committee meeting on Zoom where we talked about the Astrophotography workshop and also the emergency management plan that Phil and Mark and Ali have been working on. We've also had a second year 10 student approach us to do work experience later in the year, but they ended up pulling out because they couldn't come on the dates when we can fit them in, unfortunately. So we have one year 10 student who'll be doing stuff here in August. And we also talked on the committee about getting an 11-inch Meade Schmidt-Cassegrain telescope, which we're in the process of doing. 25th and 26th of April, which was the weekend, we had Sterling calisthenics here and 30 young women, and we showed them the night sky on the Saturday night, and they were very lucky to have no cloud, and special thanks to Phil Peters for providing on-call support during the weekend to keep them going and opening up and closing. Public night on the 1st of May, Chris gave the talk. It was definitely Chris's day for talks that month. He had 85 visitors and 80% cloud, and unfortunately the rest of the cloud followed. The following day he had one group of Freemasons here at the Briars, 100% cloud. The week after is at Gregorius Lodge up in Melbourne, had about the same number of visitors and 100% cloud again, so even if they'd wanted to look through the telescopes, they weren't going to see very much. Then on the 9th of May, we had, as you can see from the picture in the background there, some of us went up to see Brian Cox. At least one, Sylvie, went to see him just the other day at a different time, up at the Melbourne Convention Centre. We had 9 members turn up for that. 10 were going to, because one forgot to turn up on the evening, and received this horrific phone call from me saying, "Where are you? Where am I? Why? Why? Why are you asking? Because you're meant to be up here seeing Brian Cox. So anyway, one missed out, and you could hear the wails of anguish over the telephone as they realised that they weren't going to get there to hear him. All very good there, and I'll send something out on eScorpius about that in the next day or two, because it was a lot. I actually found the talk a lot better than his previous one, a lot more technical. And there's a lot of philosophical stuff in there as well, and as to why things are the way they are. So coming up in the coming months, we have this Saturday, we've got the Working Bee and Members Barbecue here at the Briars from 4 o'clock as usual. Next Wednesday, the committee meeting by Zoom. 29th of May, which is Friday, not this Friday, but the following Friday. We've got the next SCAG night, Scouts, Cubs and Guides. At the moment we don't have any bookings, so that may be called off at the last moment if we remain to have no bookings. Otherwise we will go ahead, even if we only get one turn up. 30th of May, that Saturday, we've got the Cosmology Discovery Group here at the Briars, and that's Saturday afternoon. 5th of June, Manfred's going to be talking at the Public Stargazing Night, and he's got 97 booked for that one already, so it's going to be a pretty full night for that one. Then the week after, on the Friday, we've got the Indigenous Astronomy night here at the Briars, if Tim Patson is okay to come to that. Still fairly low booking at the moment for that one, so hopefully that picks up in the next couple of weeks. Before the next Society meeting on the 17th of June. Then immediately after the Society meeting the next day, we've got the Mornington Scouts here at the Briars the next day. And the day after that, I believe we've got the Echo House have their winter lantern making event as part of the winter solstice celebrations, and they'll be here on the 19th of June, and I think probably there's only going to be a handful of those people, maybe 30 or so, I would think. It was about that number last year, I think.
Welcome to Astromofo number 31, the Milky Way. So this month's challenge was to capture the Milky Way in our photos, and our esteemed president managed to capture this shot of a bunch of happy bunnies at MPAS, having a look around the Milky Way. So what camera did you use for this one, Pete? Can't remember? I think this one might have been an artificial intelligence camera. I just posted this because the Briars was scheduled to have bunny population control measures in place around the 20th, which were luckily cancelled, so the bunnies were happy about that. And by population control, I don't mean they were going to separate the boy bunnies from the girl bunnies. I think it was going to be a bit more drastic than that. But anyway, it means we got to come down here. A few members managed to come down here and shoot some photos. First photo I'll start with was sent in by Fred Prudder, but this one's not eligible for the challenge because he did capture it a few years ago. But the reason I'm showing it is because it shows a phenomenon known as airglow. And that's that green colour that we see low on the horizon. And airglow is caused by the atmosphere becoming ionised during the day from the solar UV and also from cosmic radiation, splitting nitrogen and oxygen and ionising the atoms. And then at night, we see that as a faint glow in the upper atmosphere. And this generally happens pretty high in the atmosphere, about 80 kilometres and up. So thanks, Fred, for sending that in. But one that Fred did send in that is eligible is this one here. So members who completed this challenge were Fred, Sylvie Grandit, Mark Stevens, Greg and myself. And this one here was taken near Nombi, near Coonabarabran. Pretty dark skies out around there, and Fred was out there a few weeks ago and he captured a couple of shots. This one here showing the Southern Cross and the pointers on the lower left and the Magellanic Clouds on the right, which is a pretty nice photo. And then this one here with some foreground light painting as well, taken with an OM camera and Leica lens. So thanks, Fred, for those. This was Mark Stevens' one, although I think technically just scraped in because of the narrow field of view. But he did attempt a mosaic with the sea star, so there's a couple of panels here. So he's got the Coalsack Nebula and Acrux on the right there, and that little star cluster on the top left is the Coalsack open cluster. So well done, Mark. Yeah, it was. I thought I'd put it in there for you anyway. Mates rates sort of thing. I've got quite a few photos from Greg, or a few photos anyway. These are shot with a 135mm lens, which give a really nice sort of field of view. So he's managed to catch the whole Southern Cross in the photo and part of the Coalsack Nebula there. And this sort of field of view really lets you get a whole bunch of different objects in the field of view. So the stars of the Southern Cross, if you don't know, are labelled Alpha, Beta, Gamma, and Delta Crucis, and Epsilon there in the between Alpha and Delta. And they are Alpha, Beta, Gamma, Delta is the order of their brightness, and it also just so happens that going around clockwise from Alpha, you go from the brightest to the dimmest as well. So again, we've got the Coalsack open cluster there in GC 4609, and also just below Beta Crucis there we've got 4755, which is the jewel box cluster as well, which is a very popular target. Another one here by Greg, again same equipment, and we've got the Eta Carina Nebula and the gem cluster up there, and then the southern Pleiades over there, IC 2609, and another couple of clusters, open clusters in the view as well. And this one here I really like. We've got Omega, Centauri, and Centaurus A, so the globular cluster and the galaxy both in the same field of view. So thanks, Greg, for that. And another one here is also around open clusters, and it's near the Running Chicken Nebula. Is where this one here is, and the two, hang on, is it? Close. 4609. Anyway, here we go. Wrong way. Yep, there we go. So there's a few other clusters over there. Gum 45 and Gum 41 and Gum 39, I always think of as the chicken's feet with the chicken running, but that's that area there. I think I'm in the right neighbourhood. Pardon me. M8 and M20, the Lagoon and the Trifid Nebula as well, with a 135mm lens from Greg. And another one of the Eta Carina Nebula, the Pincushion open cluster as well up the top there. So well done, Greg. My effort was trying to stitch together a panorama of the Milky Way. So on that night when the bunnies were celebrating, 20th of the 4th, I managed to capture 4 panels of the Milky Way with a fairly wide lens. It was a 10 to 20mm lens set at about 17mm. And I started off on the right side, which is that bright star on the right is Sirius, and then sort of made my way photographing across the Milky Way. So just Sirius was pretty low on the horizon, so that panel had a fair bit of glow in it, and then getting each subsequent one all the way across to the eastern horizon, where Scorpius was just coming up. So that's Antares on the far left panel over there. And I managed to stitch that together somewhat to create a fairly wide mosaic, which I'm planning on adding to as we go. So one thing I haven't perfected is getting these panels stitched together in a way that they don't show up, but time to work on that. But also just in the previous one, so up the top we've got our view of the Milky Way, the looking down view of the Milky Way, and the red lines, between the red lines is sort of the field of view that panorama shows. So not quite into Sagittarius, but I suppose coming up now we'll might be able to get another panel to add to it. So ideally I'd probably go around all the way around and get as much of it as I can. Hang on, go back again. The part of the Milky Way that we don't see is usually up around about sort of this part of the Milky Way here is part that we don't see, sort of stays below the northern horizon, but pretty much the rest of it we get a pretty good view of from the south. And the last one from, this one was from the 11th of May with a 70 to 220 mil Nikon lens, so about 155 millimeter focal length of the Vela supernova remnant in Vela. Sylvie sent in a couple of pretty nice ones taken here. So this one here, we've got our rocket in that photo there, and our favourite gum tree. Nice view of the Milky Way there. And I like this one. The silo, green silo, taken by Sylvie as well, with a Nikon 5500 and a 14mm Samyang lens. So good stuff, Sylvie. And this one here from the balcony. So those three images were from Sylvie, and that's all we have for Astromofo. Our next challenge is going to be imaging Antares. So Antares, the yellow star, the heart of the Scorpion, and we've got a pretty colourful part of the sky there with the Rho-Ophiuchi cloud complex. But you can photograph it with any equipment you want, any field of view you want, as long as your image has Antares sitting in there, you can submit it for Astromofo. I've also collected, just to show, photos of the comet that everyone took. I think I've collected everyone, and if I've missed any of them, I apologise, but there's a few pretty nice one here. So Comet C2025 R3 Pan-STARRS was a long period comet originating in the Oort cloud, and it was discovered by the Panoramic Survey Telescope and Rapid Response System in Hawaii. So that's where the Pan-STARRS comes from. And the C in the name comes from the fact that it's an open orbit comet. Designation C means we're not going to see it again, or it's not coming back for a very, very long time. Periodic comets have a P in front of them. Comets that are destroyed by the sun or crash into something are designated with a D in front of them. Another one by Amy Tang of the comet as it's going past SAFE in Orion. And this was on the 11th of September. The comet was discovered on the 11th of September 2025, and that's where the R comes from in the name. So R, the letters after the 2025 designate what time of the year it was. So A, B are in January, C, D are in February, E, F are in March, and so on. And R means it was discovered in September, and it was the third comet discovered in that time frame. The only letter that they don't use when designating comets is I, because it might get confused for a 1. So Andrew Nilsson captured this one with the comet going past M42 there, and 16 stacked shots of 15 seconds each. Capturing a nice one. And what else have we got? A couple by Greg as well. So the comet passing through Orion, captured through the clouds there. And if we zoom in, that's where we have the comet, and that's where we have the Orion Nebula. A couple more by Greg here as well, imaged with the 200mm Newtonian and the Meade, 14-inch Meade at the observatory. And Lee Hornsby captured this image as well. This isn't a stacked one, it's a single 5-minute exposure of the comet on the 11th of May. At this time, the comet was around about 122 million kilometres away and still moving further away. So it's on its way out of the solar system, probably never to return. Maya captured this one from the observatory as well, and I believe it was using the 125mm refractor on the 12th of May. So nice one there by Maya. And Michelle sent in a couple, one of them captured by her son using the Sea Star. So he took the controls of the Sea Star, and that's the one on the right, captured by William, so I was pretty rapt about that. And the one on the left is also Sea Star. Yep. Sent in by Michelle as well. So some really great images there. Thanks, Michelle. Phil Holt captured this one as well on the 10th of May, and it just shows the comet just right about there. If you can sort of just make out the little green blob there. The comet's green because, does anybody know why the comet's green? When the sun hits the comet, it creates the coma, the atmosphere around the comet, and a lot of the times that contains carbon molecules. Usually diatomic carbon is what gets ionized, and when that's ionized, it tends to glow green. So that's where the green color of the comet comes from. It's ionized diatomic carbon in the coma, and then going through the tail as well. And this was mine from the 11th here at the Briars as well. So a stack of about 45 images with the Orion Nebula on the left, and the other one on the right is just a single one. I kept single shot from that night with the comet up here and capturing a few satellites streaking through in that period. So that's about a 60-second period where those trails are coming through. And that's it. Thank you very much, and well done to everyone for all those images. Good job. Any questions?
The question I've got, Chris, we've seen comets and shooting stars and asteroids. Is there anything in that sky when it comes to UFOs that the general public or NASA don't know about? There are still things in that sky we don't know about.
Yeah, I think usually if it's got a U in front of it, they don't know about it. It's the unidentified is the U. So things that usually they see that they don't know what they are, they'll classify them as a UFO. It's pretty much what it means. But the other thing is we know what we know, but we don't know what we don't know.
Actually, name and say this is something from wherever, or this is a new form of a rock or something like that.
There's interstellar objects which.
Oh, yes. Yeah, there is. There was the Haumea, that asteroid, the interstellar visitor. There was a lot of media hype about that one, saying that may have been an alien starship or something like that. And then you get all these AI images coming up on social media saying NASA captured this photo, but NASA never captured that photo.
Speed up on the way out.
Maybe. Yeah, it saw what was living here and thought, yeah, I've got to get out. Thanks, Fred. Anything else? All good? Cheers. See you next month with your photos of Antares.
Well, actually, I've got a question.
Yes.
What's the brightness of the comet?
Oh, at the moment, at its peak it was +3, which was when it was perihelion. And now I think it's dropped down to below 12.
Was it ever naked eye visible?
I don't know. I don't think so. I don't know if it was at all naked eye visible when it was on its way in, but so it was visible in binoculars though. There's a few people that were spotting it with binoculars, and obviously with the telescopes here we were able to see it. But I don't know. I didn't hear of anyone seeing it naked eye. Yeah. All right, thank you.
All right, welcome to Sky for the Month. Maybe you can already guess from the city behind me. I'm in London, so to be more precise, I'm at Greenwich Observatory this month, and having a look around here. It's a fantastic place, a really nice museum, and I'll show you some of the other things we can see here right at the end. But let's first look at the solar system from the top. Let's start with a look at the inner solar system. So as you can see, Venus here is almost at a 90-degree angle to the sun, which means that it's basically at its highest that it will be as seen from Earth. You can also see that Mercury is basically hiding behind the sun now, so it's just coming out of its superior conjunction when it's exactly in a line behind the sun as seen from Earth. Mars here is in the morning sky, so this part of the sky is the morning sky, and it will also rise a little bit earlier every day over the next few months. So zooming out to the outer planets, the first thing to see is that Jupiter here is almost on the same line of sight as Venus before, and we will see what that looks like from Earth in a few minutes. Saturn, a morning object here, Neptune, also a morning object, and Uranus at its conjunction with the Sun, so hiding behind the Sun. Now, zooming back in and then having a look at the situation over the next month, we'll see that Mercury is very fast, right, as always. So it only takes 88 days in its orbit around the Sun. And you can see that it's going to reappear in the evening, while we are also catching up with Mars, so Mars will rise a little bit earlier, as I said earlier. So having a look at the all-sky view on the 1st of June, the evening of the 1st of June. So this is around 5 p.m. We're heading towards the winter solstice, so the days are pretty short. Sunset is around 10 past 5. And we can see just after sunset here that both Venus and Jupiter, as I said earlier, are in a very similar position in the sky for us. So Jupiter setting around 8 p.m. now, and Venus also a bright evening object. The other thing you can just see here is that Mercury is about to set, but on the 1st of June, it's just come out of its superior conjunction, so just reappearing from behind the Sun, and it will also be an evening object over the following few weeks. You can also see that the Moon is just about to rise here in the southeast. So we've just had the new moon on the 17th of May. The full moon will be on the 31st of this month, and then the new moon again on the 15th of June, and another full moon on the 30th of June. Now winding the clock forward a bit to around 10 p.m. and we'll have a look at the brightest stars in the sky. So let's orient ourselves. The bright star here high in the north, that's Arcturus. And then if we drop down to the western horizon, we see Regulus in Leo here. So the last of the kind of autumn stars, basically on their way out now. And then here, very close to the meridian here at 10 p.m., we have Spica, which is the bright star in the constellation of Virgo. And of course, here slightly further east, we have Antares, the heart of the Scorpion. And here, center stage, almost at the zenith, so it's the zenith right here. We have Alpha and Beta Centauri, the two pointer stars, and then the Southern Cross around here. So this is about as high as the Southern Cross will get. If we drop down to the southwestern horizon, we still have Canopus in the sky here, the second brightest star. And then towards the south, very low towards the horizon, we have Acana. And you can just see Altair rising here in the east. So that's the first star of the summer triangle, the northern hemisphere summer triangle. And the other two will rise a little bit later at night. So the main constellations, of course, are Centaurus and Scorpius, now very prominent here in the center, almost around the zenith. And of course, that means that the core of the Milky Way is straight above, and we have the entire plane of the galaxy here stretching out over the entire sky. And we can see that over the next few hours here, if I fast forward towards the morning, the Milky Way really beautifully spanning across the entire sky. So around 2 a.m. we have Neptune rising, and then closely followed by Saturn at 2:30. If we wait a little bit, we will see Mars rising around 4:30 or so. So those are all morning objects at the moment. And then just before sunrise, we see Uranus that has just come out of its conjunction with the Sun, which was on the, or will be on the 23rd of May. Sunrise on the 1st of June is around 7:26 a.m. A quick look at the apparent sizes of the planets on the 1st of June. Nothing too interesting here. Jupiter is getting smaller, Mars is getting larger over the next few months because we're catching up with Mars and losing Jupiter a little bit. Mercury also, this is on the 1st of June, but it will get larger. As we saw earlier, it basically reappears from behind the sun at the moment. Now, to the conjunctions, we have really nice conjunctions with Venus, Jupiter, and the Moon. So the first one here is where the Moon gets really close to Venus and Jupiter on the 20th and 21st of May, so basically today. This is just after sunset. Looking towards the west, we'll see Venus, a crescent moon, and then Jupiter. So if you missed that today, you've got another chance for a really nice conjunction. Basically, if you look at this part of the sky every day now for the next couple of weeks, you will see Venus rise a little bit higher every day and Jupiter basically be a little bit lower towards the horizon every day. And then on the 8th or 9th of June, they will be very close together within 1.7 degrees of each other. So that should be really nice to observe around that time. Finally, comets. We have only one comet in the sky at the moment that's worth mentioning. That's Pan-STARRS. We already had that one last month. It's now fading a bit. It was actually really bright. We saw some very nice photos on eScorpius and Facebook, so make sure you look those up. But it is fading now a little bit. It was in Orion, so very interesting photos with the entire constellation of Orion and then this comet in the background. So let's take a look around Greenwich Observatory. This is the Meridian Courtyard with the Camera Obscura and the famous time ball, which we will see again later. And this is called the Meridian Courtyard because it's where the prime meridian was defined. So here you can see me hopping over the prime meridian from west to east. And these meridians were defined using meridian telescopes such as these, which are used to measure the transits of stars across the meridian. So famous people like Halley, for example, worked here and worked with these meridian telescopes. But Greenwich also has a great refractor telescope under its main dome. This is known as the Great Equatorial Telescope. It has a 28-inch objective lens and a 28 feet focal length. So that's 71 centimeters and 8.5 meters. And this is one of the 10 largest refractors ever built from 1893. The main reason this observatory was built was to find a method for determining longitude while at sea. And that's why they also have a collection of very famous clocks. And so these are two of the most famous clocks in the world, probably, the H3 and the H4 by Harrison, the first successful marine chronometers. So talking about time, it's almost 1 p.m. and at 1 p.m. every day, the time ball is dropped so that ships in the harbor could synchronize their chronometers with the official Greenwich Mean Time. So there we go.
All right, that's all for this month, and I'll see you next time.
Tonight's feature is all about neutrinos, the universe and everything, given by this lady here, Associate Professor Kirsty Duffy. She's a particle physicist at the University of Oxford, and she's also working with Fermilab, which is in the United States, as a collaborator there on the June project, looking into neutrinos, as well as the Microboon international project as well, for which she's the team leader. Now, this public lecture was held only a couple of days ago, and like here in this room, they do have some microphone difficulties, so I'll turn up the volume and hopefully you'll be able to hear it. Some of the questions, for example, are a little bit hard to hear at the end, primarily because I think either they didn't switch the microphone on as they went around to put it in front of the person, or they didn't bother with the microphone. So this goes for about an hour with half an hour of questions. So if you wish to get up and have a cup of tea or whatever, have a break, feel free to do so. Just quietly leave and then come on back in.
My name's Kirsty. I'm a particle physicist in Oxford, and I study particles with neutrinos. So over the next hour, I'm going to talk to you about what these particles are, why they're interesting, some of the mysteries that they've posed to scientists over the years, and some of the big questions that we think they might be able to solve, and how we're trying to solve them. So particle physics, I started with this picture because particle physics is about asking the big questions about the universe. What are we made of? Why are we here? Where did we come from? Why did the universe exist? Obviously, the first one, what are we made of, is very solidly in the realm of particle physics, but I will argue that some of those other questions are as well. And in preparing for this talk, I've been thinking about what first got me interested in particle physics. And I think I can trace it back to a book that was really formative in my childhood and set me on the career path I have today. It is this book. This is the Smarties book of all the incredible facts you ever need to know. And it has some really great facts in it. Apparently, there was a flight sergeant in 1944 who fell out a Lancaster bomber. Well, his Lancaster bomber was on fire. He ejected, the parachute didn't work. But he hit trees on the way down and landed in a snowdrift and was fine, no injuries. Also, it taught me that a cockroach can live for a year without a head, which is terrifying. And more importantly, it taught me that everything is made of atoms, and that atoms are made of smaller particles, protons, neutrons, and electrons. And I was probably like 7 or 8 when I had this book, and I was really taken by that idea that everything is made of atoms. And at the time, I thought atoms was just one thing, right? And so I was like, how can everything be made of one thing? And how does the atom know what it's meant to be? How does it know whether to make a butterfly or a table? And then it's weirder because then those atoms, it turns out, are made of 3 smaller things. So we've sort of gone in and then we've gone out again. Is that it? Does it go back to one thing again, or are there more? We now know, well, I now know, this is the periodic table of elements. So these are all the atoms we know about. There's not only one type of atom. 7-year-old Kirsty was not entirely on the money. There's sort of 200-ish. But all of these are still made of protons, neutrons, and electrons. And so, you know, my question sort of still stands is, A, it's super weird that these 3 things make so many different things that we can see. And B, like, are those the smallest things then, or are there smaller things that make those? So it's been nearly 30 years and multiple degrees. And I can now tell you, this is the particle physics version of the periodic table. We call this the standard model of particle physics. And this shows what we think are the fundamental particles that are not made up of anything else. So it's sort of arranged in a box which has quite a lot of meaning. But you can see at the top there's purple particles labeled quarks. And at the bottom there's green ones labeled leptons. Those 12 particles we think are all the particles that make up everything. There's then these sort of red guys on the side, labeled gauge bosons. Those are the force carriers that transmit forces between particles. And then there's the Higgs boson, which is how particles get. So our protons, neutrons, and electrons are in here, sort of. You can see the electron. You can't see, oh, I have a laser pointer. Does that work? Okay, you can't see the protons and neutrons because it turns out they are not the smallest things. They are made of up and down quarks. But these are the things, despite knowing about all these other particles, these are the ones that make up everything. Looking along the table, each column in this table, we would call a generation of matter. So our first generation of matter has our protons, neutrons, and electrons in, or our up and down quarks and electrons. If we focus just on the electron, if we go to the one next to it, which is the second generation of matter, that is called the muon, and it is basically the same as the electron, but 200 times heavier. So it has, electron has charge -1, the muon has charge -1. It does all the same types of interactions that an electron will do, but it's a lot heavier. Similarly, in the quarks, we have charm and strange quarks, which again behave very much like up and down, except they're a lot heavier. And then we go up to the third generation, where again, the top behaves like up and down, the bottom behaves like top behaves like up and down, bottom quark behaves like down and strange, and the tau lepton behaves like the electron and muon, but again, heavier. The muon is about 200 times heavier than the electron, the tau is about 200 times heavier than the muon. So, then finally, we get to our neutrinos, which are the ones I'm interested in. So you can see we have 3 neutrinos here, the electron neutrino, the muon neutrino, and the tau neutrino. And the different types we call flavors. And the flavor is denoted by a little subscript for each electron, mu, Greek letter mu for muon, and Greek letter tau for tau. You can see they're sort of, in the way this is laid out, they're paired with the lepton that has the same flavor. And that is by design. The standard model, as far as we know, really pairs neutrinos with what we call the charged lepton partner. And that, it turns out, is really important. Okay, but before I get to that, you might well be looking at this and saying, you just told me everything I've ever seen, heard, felt, smelt, touched is up, down, quarks, and electrons, and neutrinos is none of that, so why should I care? Neutrinos are, by far, the most abundant matter particle in the universe. For every proton, neutron, or electron, there are about 1 billion neutrinos. If you hold out your hand and look at your thumb, every second, about 100 billion neutrinos pass through your thumb. And they're not, magically focused on your thumb. They're streaming through all of us all the time. They come from all over the place. So neutrinos were created in the Big Bang, and there are still neutrinos around today that were created in the Big Bang. About 300 per cubic centimeter on Earth. Neutrinos from the Big Bang are passing through us. This is not the topic of my talk. Super cool. If you could measure these neutrinos, you could see the conditions of the universe a second after the Big Bang happened. By comparison, if you know about the cosmic microwave background radiation, that is like years after the Big Bang happened. So it'd be really cool if we could measure these neutrinos. We haven't worked out how to yet because they're really low energy, but if we could, it would be awesome. We get neutrinos in supernovae when a star explodes. So in fact, about 99% of the energy of a supernova is carried away by neutrinos. And the neutrinos from a supernova reach the Earth before the light does. So if you could detect the neutrinos, you could point your telescopes in the right direction and see the start of the supernova, which would be super cool. We've only detected supernova neutrinos once, but we're all really excited and slightly on edge every time we turn a detector off, just in case that's when it happens again. Most of the neutrinos that are passing through you at the moment are from the sun. The sun creates 10 to the 38, so that's a 1 with 38 zeros after it, neutrinos per second. And this was used for one of the very first neutrino experiments that was a huge mystery in particle physics, and I'll talk about that a bit later. We also have them coming up from the center of the Earth, the plasma in the center of the Earth, the interactions that are happening there are producing neutrinos. We can create neutrinos from man-made sources like nuclear reactors and particle accelerators. This is a photo of Fermilab, which is a particle accelerator lab in the US, and it's one of the sort of 2 big places that we produce neutrinos in the world. And in fact, you get neutrinos anytime there's any sort of radioactive decay. So bananas, very high in potassium. Potassium is slightly radioactive. Reasonable source of neutrinos. Also a source that's close to my heart because I host a YouTube video series called Bananas on the Fermilab. Okay, so if there are this many neutrinos around, why have you never seen one? Does anyone want to guess? They are invisible, yeah. This is a big problem. Anything else? Super light, yes, yeah. Yeah, barely having mass, yeah. Also makes them hard to see, yeah. Yes, neutral, that's a problem. I'll talk later about how we detect neutrinos, all of these issues. And so for all of these reasons, they basically never do anything. And when I say basically never, 100 billion passing through your thumbnail every second, in your entire lifetime, 1 or 2 will probably interact with an atom in your body. The rest of them just pass straight through you like a normal. My colleagues who work at CERN think of neutrinos as missing energy, where they're literally defined by the fact that you don't see them. Yeah, and for that reason, they are often called ghost particles. Now, you might have noticed that the title of my talk is a Douglas Adams reference. If you're asking, did Douglas Adams know about neutrinos? The answer is yes. Here's a Douglas Adams quote: "The chances of a neutrino actually hitting something as it travels through all this howling emptiness are roughly comparable to that of dropping a ball bearing at random from a cruising 747 and hitting, say, an exit." So I will say you are a more knowledgeable audience than most. A lot of the time when people talk about why neutrinos almost never interact, one of the things they say is just because they're really slow. And when I say some people, I mean me. So I have said in talks like this, you know, most of an atom is empty space, and neutrinos are so small that they just go through that empty space. And that's sort of true, but it's not technically true. And I think we all agree that technically correct is the best kind of correct. So technically, neutrinos are not very small because neutrinos don't have size. So the standard model says that all our fundamental particles, all the particles I showed you in that table, are what it describes as point-like, which means they don't have a size, they're just a point. I like to imagine it like you know, dotting a pen on a piece of paper, and it's just a point that I make. I don't draw a circle and colour it in, I just dot a point. But obviously that is actually huge. That point has a size and it's very, very big. I will also say that point-like is really hard to find pictures to put on a slide because anything really small you wouldn't be able to see. But this is a nice sort of way of visualizing it. So this is what we would expect from a normal particle, or not a normal particle, a normal object, anything that has any kind of state. So the black circle here is what we would consider the particle, and the red around it is where you might feel the forces from that particle. So say this is an electron, it's got a negative charge. If you bring another negative charge particle close to it, it's going to get repelled. And this, we can visualize this red as sort of where that repulsion might be. So when it's very distant, it looks like the particle is a point, but you can sort of feel the forces if you get close enough. If you get closer, the particle looks bigger, and if you get even closer, the particle looks bigger. I don't really need to explain this too much because this is how everything works. Things that are closer to you look bigger. For point-like particles, no matter how much you zoom in, it still looks like a tiny point. And so even when you get closer, you might feel the sort of force field seems to get bigger. The particle itself still seems to be a tiny point, as the smallest point you can imagine. Okay, so why then do we say that neutrinos in particular are really small? To answer that question, we need to talk about how we think about size in particle physics. And for that, I have a demonstration with beach balls. I'm going to need some volunteers. I'll take you two, please. Okay. All right. I'd like you to take your ping pong balls, stand back, and then when on the count of 3, I want you to throw them at each other and try and hit the ping pong ball together. Ready? Okay. 1, 2, 3, go. Okay, you've got 3 ping pong balls, so we've got 3 goes. Don't worry, we'll pick them up at the end. All right, second go. 1, 2, 3, go. Close. You're getting better. Okay, let's try one more. All right, 1, 2, 3, go. Okay, now we're going to try the beach balls. So do you want to go grab those beach balls over there? If you're feeling confident, you can stand a little bit further. Okay, you ready? 1, 2, 3, go. All right, let's try that one again. Yes, you're not really proving my point. All right, 1, 2, 3, go. Yay! Well done. Okay, that is it. Thank you very much. You can see that. Okay. Which one, to my volunteers, which one was easier to hit together? Yes. Slightly harder question, why? Yes, exactly. So they were bigger, and specifically, actually, what matters when we say they're bigger is what we call the cross-sectional area. So that is the area of the 2D circle that you can see when the ball is flying. If you are inside of that 2D circle, you're going to get the ball. And if that 2D circle is bigger, then you're more likely to find it. So we can say if it has a bigger cross-section, then it is more likely for the balls to hit, which in particle physics terms we would say is more likely to hit that. In particle physics, nothing has a size, but we can define a size by reversing this logic and saying we can calculate how likely a particle is to interact, and therefore we define its cross-section and say how big it is. And so people say neutrinos are particularly small because they are very unlikely to hit that, whereas people might say that protons and neutrons are bigger because they're more likely. So the reason for that is comes down to the forces that neutrinos interact with. So these are the four fundamental forces of nature. We have the strong nuclear force, which is the force that binds quarks together to make protons and neutrons, and it binds protons and neutrons together with the nucleus. We have the electromagnetic force, which is the repulsion between two charges that are the same or between magnets. We have the weak nuclear force, which again happens in nuclei but is weak. And then we have the gravitational force, which I'll be honest, as particle physicists, we don't really know what to do with. We haven't worked gravity out yet, but we're willing to acknowledge that it's that. In terms of the strength of these forces, the strong force is by far the strongest one. The electromagnetic force is next. The weak nuclear force is next, and gravity is the weakest force. That is sometimes surprising when you tell people that gravity is the weakest force, because gravity is the force that we sort of experience the most in the world. And we tend to think that it's quite a strong force. Gravity is the reason that I can't fly. But that gravitational force is between me and the entire Earth. I am not feeling any particular gravitational attraction to this bottom of dipeptide. And actually, the reason you are not falling through the seats towards the center of the Earth is the electromagnetic force. The atoms in your clothes are repelling against the atoms in the chair electromagnetically, and that is overcoming the gravitational force of the entire Earth. So gravity is really super weak. The problem for neutrinos is the only forces they experience are the weak force and gravity. And so they almost barely interact because they can only interact very weakly, and they're very unlikely to do so. If we were going to do this size comparison with the beach balls and ping pong balls properly, if an electron was the size of one of these beach balls, they're just over an meter across. A neutrino would have to be the size of a grain of sand, about a millimeter across. So they interact much, much less than any other. Okay, so now that we have established that neutrinos are both very small and exactly the same size as the other particles, I want to talk about what's really interesting about them. So a quick reminder, we know about these three types, electron, muon, and tau neutrino in the standard model. And that is, for a while, we thought those are three distinct particles, just like how, up quarks are different from down quarks and electrons are different from muons. It turns out it's not quite the full story. So back in the 1960s, there was an experiment to measure neutrinos from the sun. We know that the sun is a huge source of neutrinos on Earth. Neutrinos were first detected in the 1950s from a nuclear power plant. And so there was this idea to measure solar neutrinos. The way the sun works is the same way all stars work, is they fuse nuclei together and they are powered by that fusion energy. Our sun in particular generally is fusing hydrogen nuclei together to make helium. That is approximately the extent of my knowledge of how the sun works. Other than I can tell you there are a few different methods for how exactly that fusion goes. This is just one of them. But the important thing is that a byproduct of all the methods is neutrinos, and specifically electron neutrinos. Which also gives me an excuse to show you this cool photo. This is a photo of the sun. It might look to you like a particularly lovely photo of the sun. This is a photo of the sun taken at night from the other side of the Earth using neutrinos. So this is neutrinos from the sun that have traveled through the Earth, not stopped because they don't get stopped by stuff, and then be detected in a neutrino detector. And someone pointed out yesterday that I shouldn't call it a photograph. This photo gives you photon that's light, and so we call it a neutronograph or a neutrinograph. Okay, but this is the experiment that they built to measure these solar neutrinos. Just as an aside, this experiment was awarded the Nobel Prize in 2002. Ray Davis was awarded it, leading this experiment. So what you're looking at here is a huge tank of dry cleaning fluid, which I am artistically representing like this. So it's full of dry cleaning fluid, which crucially contains a lot of chlorine. And they're trying to measure neutrinos from the sun. We know that there are only electron neutrinos produced in the sun. And we also know that if an electron neutrino interacts with an atom of chlorine, it will turn it into an atom of argon. So the idea was that they would run this huge detector, they would look for argon atoms, and that would be evidence of neutrinos from the sun. Okay, so now we talked about how neutrinos almost never interact. Here is another example. Out of the 600 tons of cleaning fluid in that detector, they expected about 36 argon atoms per month. So it's an incredible needle in a haystack experiment to do. Nevertheless, they did it, and what they found was about half the number of argon atoms they were expecting. And this became known as the solar neutrino problem. The first suggestion, I think, is probably the one most of you are thinking, which is you were looking for 36 atoms in 600 tons. You know, good job, but it's not that surprising that you didn't get it exactly right. It was a very difficult experiment to do. So many people at first thought, you know, the experiment was wrong. That turned out to not be the answer. It's been confirmed by multiple experiments since that those results are right. So the next proposal was, well, how well do you really know what's going on in the sun anyway? It's not like we can go there and check what the fusion processes are. So, you know, maybe we just don't fully understand. The models are not that good. The data doesn't match the models. Maybe the models are rubbish. It turns out that is not the answer either. So we now know the answer, and it is much more strange than anyone originally thought. So as I said, only electron neutrinos are produced in the sun. We now know that as they travel through the sun to Earth, they change into the other photons. So by the time they reach us on Earth, only about 40–50% of the neutrinos are still electron neutrinos, and the other ones are changing into the Earth. Some people are nodding, you've heard this before, but let's take a moment to recognize that this is really weird. It's like if you're throwing a ball to your friend, and as you throw the ball, it changes color from red to yellow to blue and back again. It doesn't really make any sense, and it really didn't make any sense with our understanding of the standard model at the time. The best analogy that I've heard for what's going on is this. Imagine you have a pair of glasses that someone has put duct tape over so that there's just a tiny slit in the middle, and when you look out, all you can see is this like little sliver of the world. Now imagine you're holding a beach ball, but because you've got your stupid glasses on, all you can see is a little sliver of the top of the ball and it looks red. So as far as you know, you're holding a red. You throw your ball to your friend, who is wearing the same type of glasses. When she looks down, she sees blue, and you think, oh my gosh, this ball has changed color. We've got a magic ball. This is amazing. We're going to be rich. We've broken the laws of physics. But of course, you don't have a magic ball. Unfortunately, you're not going to be rich. What you have is a beach ball, but the way you are able to measure that beach ball isn't able to reflect the sort of full nature of the thing. And that is actually very close to what's happening with neutrinos. I want to take a small diversion to talk about how we detect neutrinos. This is a picture, actual data from an experiment I work on, of a neutrino passing through a neutrino detector. Can you see it? No. Okay, I didn't block out the picture properly. Yeah, so we have never built a particle detector that is able to see a neutrino, even a neutrino detector. All we can see is, if we're lucky, the neutrino interacts with particles in our detector and produces charged particles that we can measure. So here, this is genuinely data from my experiment. I've labeled where I think the neutrino is coming just by looking at conservation of momentum. It looks like there's a load of stuff going that way, and so there must have been something invisible came in from this side and hit it. And then you look at the particles and you try and work out what kind of neutrino interacted. You have to know what you're looking for, but in our experiments, really long straight tracks tend to be made by muons. So I've sort of labeled on here, this big long track here, and I've got a lot of probablys and I thinks because this is data, I don't know what it really is, but I would call that a muon. I think that's important there. These shorter straight tracks that are slightly higher colours, that's what protons tend to look like. So I think this is a neutrino that's interactive. It's kicked a couple of protons out of the nucleus, and it's produced a muon. And in the standard model, we sort of say by definition, if it produces a muon, it's a muon neutrino, because the standard model pairs the neutrinos with their respective charge atoms. This is another event from my experiment. This big thing here that is very much not a long straight track, in the experiment we would call it a shower. And that is what electrons look like. So again, I think we're looking at a few protons and then a big electron. And so I think that's an electron neutrino. And this is sort of the equivalent, I see an electron and I say it must be an electron neutrino, is the equivalent of I look down with the glasses and I see blue and I say, well, it must be a blue ball. So when we measure it, we can only ever see one plane. We can only ever measure electron or muon or tau. And so we say it is that one flavor. But when the neutrino travels, it actually travels as oops, let me come back, as a beach ball, which is some combination of all. It's slightly more complicated than that, as you've seen. Oh, look, I labeled it. We actually think there's 3 beach balls. Okay. So we actually think there are 3 beach balls, and I made my own here. I'm going to pass them around. I painted them and then I folded them up, and it hasn't gone great, but I think it still works. Can I throw these into the audience and sort of chuck them out? Go on. Okay. Have a look. Pass them on. Okay, so because we're really inventive and we're really good at naming things, we label these neutrinos 1, 2, and 3. And the important thing, as you'll see if you're passing these photographs, is that each of them has different ratios of the 3 different colors. And so that means that each of these neutrinos has different sort of amounts of the different neutrino flavors. So in some sense, I think we're back on slightly firmer ground. That's one way of explaining it. Okay, yeah, so in some sense we're back on slightly firmer ground, right? Because we're back to 3 neutrinos, which sort of feels right, given that we have this 3 generations of matter in the standard model. We call these beach ball neutrinos the mass states. Did I label them? I didn't. Okay, yeah, we call these beach ball neutrinos the mass states. The reason we call them mass states is when you're traveling, the thing that matters is your mass in terms of physics. So if you think about if you have a particular amount of energy and you give something a push, what determines how fast it goes is how heavy it is. If I give the same push to a supermarket trolley and a car, the trolley is going to go a lot faster and a lot further. And so because the main thing that matters when they're traveling is mass, we call them the mass states. And then these ones at the top that are are sort of the original neutrinos I introduced you. We call those the flavor states because they are the three flavors. Okay, so this is where my analogy breaks down a little bit. Oh, no, I did label them. There we go. Okay. So I said before that, you know, in our analogy, you have your glasses and you look down, and what you've got is a beach ball, but you're not able to see the full beach ball. So in that analogy, the real thing was a beach ball, and it's just that you weren't able to measure it properly. That might give you the impression that in neutrinos, the real thing is the beach ball neutrinos, the mass states, and the flavor states are just sort of, you know, impacts of the way that we're able to look at them. Quantum mechanics says that is not true. Quantum mechanics says when you look at the ball and see, oh, there we go. When you look at the ball and see red, what you have is a red ball. And the second you let go of it, it turns into a beach ball. It travels as a beach ball. And when you measure it again and see blue, it is a blue ball, which is a really weird concept. I'm not going to get into interpretations of quantum mechanics because that's a whole lecture in itself. But I will say, you know, this is called the Copenhagen interpretation of quantum mechanics. There have been people who suggested in the past maybe it's just it's not really that the ball is a red ball; it's just a reflection of our knowledge about the ball. That's a theory that was called hidden variables, and that was proven wrong a few years ago in a really big experiment about bells in the policy. Okay, but next question. If I have a red ball, and I know I'm starting with a red ball, which of the beach balls is it going to choose? Any guesses? The blue one? It's red, so it's going to be something to do with how much red there is on them. There's a guess up there. It's not quite equal for all three, but it is all three. There was another hand somewhere in the middle. Yes, yeah, it's to do with the probabilities. Okay, so nu3, as you'll see in my excellent painting, is 49% red. Nu2 is 33% red, and Nu1 is 17% red. So if we were thinking about this classically, we would say, given that I know that it's red, there's a 49% probability I'm looking at the bottom one and a 17% probability at the top one. Quantum mechanics, again, says that's not a probability that you've got one, but it is all three. It just is 49% Nu3, 33% Nu2, and 17% Nu1. And this is important because I said that these are the mass states, these beach ball neutrinos, and each of them has a different well-defined mass. I will say we don't know what the masses are, but we do know that they're different. And that's important because, as I said before, heavier things travel slower. So if you imagine you start off with a muon neutrino, it starts traveling, and it starts traveling with some combination of these three beach ball neutrinos. But as they travel, the ones that are lighter are going to slightly pull ahead of the ones that are heavier. And that means that after it's traveled some amount of time, it's maybe quite a different mixture of the three beach balls that you're looking at from the start of it. And there's a lot of maths here that I'm not going to get into, but the sort of bottom line is that the probability to measure it being a muon neutrino again depends on how far it's traveled and changes as it travels. So this is my first plot. I've only got 2 plots, but this is the first one. So this is the probability on the y-axis that you are going to measure a muon neutrino, plotted against the distance that it's traveled. So immediately after you create it, right down on the left-hand side there, you've got almost 100% probability to measure it as a muon neutrino. But as you let it travel, those 3 beach balls kind of spread out a bit, and it really changes. And you can see it almost goes down to 0. So you're almost guaranteed not to measure a muon neutrino and to measure one of the other 2 types. But then even weirder, if you go further, it comes back up again, and you're seeing muon neutrinos. And this is why this technical term for this is neutrino oscillation, because it oscillates down and back up again and down again. Okay, it's worth now proving to you that this is really what's happening, because it might sound a little bit far-fetched and like we've come up with a very overcomplicated explanation. But the Nobel Prize in Physics in 2015 was awarded to 2 experiments that really proved that this is what's really happening. So the first one here is called SNOW, Sudbury Neutrino Observatory. This is a 10-meter diameter spherical acrylic tank filled with ultra-pure heavy water that is surrounded by light detectors a kilometre underground in a mine in Canada. And so what we're looking at here is sort of the bottom of that sphere, and we're seeing the back of the light detectors on the outside. So SNOW repeated the original solar neutrino measurement, also using a method that could only see electron neutrinos, and they confirmed that they saw about 40% of the total number of electron neutrinos that you expect to see from the sun. But then they did a second measurement that was able to detect all 3 types of neutrinos, and that one got the right number. And so that was the first proof that the neutrinos are changing types and not just actually disappearing. The second experiment is called Super Kamiokande, or Super K. This is a photo of it. So this is, again, a massive tank of water underground. This one is underground in Japan. It's about 1 kilometre underground under a mountain. What you're looking, oh, and this tank is cylindrical, so it's about 40 metres across and 40 metres tall. And what you're seeing here, these sort of golden globes are the light detectors around the outside. They're all around the walls and the top of the bottom. And then it's normally filled to the top with water, but this is a photo of what they do when they need to repair. They drain the water down to the level that they need to repair. They lower a dinghy down, they get in the dinghy and they row around and pitch bits of the detector. One of the reasons I know this is the experiment I did my PhD on. I never got to go in the boat, but my husband did. And he said I could show you some photos. So this is my husband inside the detector. And this here is a video of them being lowered in. And you can see up close how big the light detectors really are. Isn't that cool? Yeah, they're about 30 centimeters across, these photo detectors. Isn't it cool? I'm so jealous. Okay. But back to science. This is my second plot. So what Super K did was a completely different measurement. They didn't look at neutrinos in the sun at all. They looked at neutrinos that are produced in the upper atmosphere. So on this diagram on the left-hand side, that's sort of showing that these neutrinos are coming from all around the Earth in the atmosphere. And they should all be muon neutrinos. So this plot on the right-hand side of the slide shows their results. They defined this direction variable, which is a little bit weird. Basically, direction being -1 is the neutrinos that have come all the way from the other side of the Earth. Direction being 0 is the neutrinos that came sideways, and direction of +1 is the neutrinos that came downwards. So the ones at +1 have travelled the shortest distance, and the ones at -1 have travelled the longest distance to get through the detector. Which, by the way, is in Japan, and I just realised I didn't make this picture, but that is North America, that's not Japan. Okay, but this plot, so for each value of the direction, they calculated what they would expect to see, the number of muon neutrinos they would expect to see if there was no neutrino oscillation, that's in blue. And then they calculated the number they would expect to see if there was neutrino oscillation in red, and then the black point showed what they measured later. And so you can see there's really clear evidence that the neutrinos on the left-hand side of the plot, so the neutrinos that have traveled further, are more likely to have disappeared. And this was the first evidence that the probability that you measure a neutrino as a particular type depends on how far it's traveled. And that's really important for confirming that it's neutrino oscillation following that sort of theory that I talked about. Okay, so we're now pretty convinced that neutrino oscillation has been proven to happen. Super cool, because this is purely a quantum mechanical effect. And we often talk about how quantum mechanics is only really applicable at very small scales. But this is a quantum mechanical interference that happens over hundreds or thousands of kilometers. It's also only possible if neutrinos have mass, because it depends on that splitting up of the different mass states. If they don't have mass, or if all the masses are the same, then you wouldn't get this. And the reason that's important is that in the standard model, neutrinos don't have mass. So the fact that we've seen neutrino oscillation proves that the standard model is wrong, and that our understanding of the universe is and if you're getting into a field of particle physics, it feels like a pretty exciting place to be starting from. It also opens the door to many more questions. If we're going to work out how to fix the standard model, we need to understand neutrinos really well. And there are many things we don't know about neutrinos. This is just a sample. How many neutrinos are there? I told you there are 3, and I will say we know that there are 3. But there's no reason in the standard model that there should only be 3 generations. So there could be more that we haven't discovered yet. How do neutrinos interact with complicated nuclei? That's important for understanding how they appear in our detector, given that we can only see them after they're detected. Which neutrino is heaviest and which is lightest? Don't know. How much do they weigh? Also don't know. We know that it's a lot smaller than all the other particles, but we don't know what it is. We don't know why it's so much smaller than the other particles. It is a lot smaller than the other particles. And it's really unclear why it would be so much different. And people have sort of hypothesized that maybe it's because neutrinos don't interact with the Higgs in the same way that other particles do. There's also, this is sort of linked to that, one of the ways that they could not interact with Higgs is if they're their own antiparticles. Super cool, not going to say any more about that, sorry. We don't know why the neutrino mixing is so large, why it does this such big oscillation. But the one I'm going to talk about for the rest of this talk that I do most of my research on is neutrino oscillation different for antineutrinos? The reason that is interesting is we think the Big Bang created equal amounts of matter and antimatter, and particle physics really loves sinning. So we think there were equal amounts of matter and antimatter created in the Big Bang. Antimatter is basically the same as matter, but opposite. So every particle has an antiparticle pair that is the same mass, but the opposite charge. And importantly, if a particle and its antiparticle come together, they destroy each other in a burst of energy. So the question is, in the 13.6 billion years since the universe was created, if it created equal amounts of matter and antimatter, why haven't they come together and destroyed each other? And why do we live in a universe that is only made of matter, and it seems like the antimatter has disappeared? The answer has to be that there's some difference in physics between matter and antimatter that has caused the antimatter to disappear more than the matter. And you only need to generate about a 1 in a million imbalance. So you could have a million particles that do destroy each other, but the one that's left over is enough to create the universe. But what we don't know is how to get a 1 in a million imbalance from the laws of physics that we know about. We have seen some differences between particles and antiparticles at CERN, but the differences that we've measured have not been enough to generate the universe that we have. And the place that we haven't looked yet is neutrinos, because they're really hard to study. But we do have a couple of hints from some current experiments that there might be differences, and so it seems like a very promising experiment. The way my work is, the types of experiments I work on to try and address this are called accelerated neutrino oscillation experiments. The way they work is this. We create neutrinos in a particle accelerator. That avoids any, maybe you don't know what's going on in the sun problems. We make the neutrinos ourselves, we know what we've made. It's also very handy that particle accelerators produce almost entirely muon neutrinos. And if you're looking to see them change flavor, it really helps if you're just starting with one flavor. There are 2 main places in the world that we have accelerators to make neutrinos. Fermilab in the US, just outside Chicago, and Tokai in Japan, about an hour on the train north of Tokyo. Okay, the next thing we do, just for good measure, is measure them immediately after we've made them in what we inventively call a near detector, because it's near to where we make the neutrinos. We just want to check that we know exactly what types of neutrinos and what energies they have before we let them oscillate. We then send them some long distance and allow them to oscillate. And a fun thing here is we're generally sending them sort of hundreds of kilometers, which is long enough that you have to worry about the curvature of the Earth. But you don't have to dig a tunnel because neutrinos almost never interact. So you just take your particle accelerator, you point the beam sort of downwards, and then the Earth curves over and the beam pops out again at the point that you need. And then we measure them again at a far detector, and we're looking to see if the neutrinos have changed. So if we started with muon neutrinos, we would be looking for those muon neutrinos to sort of disappear and different types of neutrinos to seem to have appeared. So there are two experiments that are doing this at the moment. One in Japan called T2K, which is the one I did my PhD on, and that uses super K as the far detector. And one in the US called NOVA, which is sending neutrinos from Fermilab near Chicago up to northern Minnesota. As I one thing I'll say is that it's generally very valuable to have two experiments so they can cross-check each other, especially if you're trying to make sort of big discoveries like differences between matter and antimatter that could have really big impacts on our understanding of physics. You really want to know that you've got that right, and so it helps to have another two people who've done the same thing separately and got to the same answer. Both of these experiments have seen hints of the oscillation being different for neutrinos and antineutrinos, but they don't have the precision to really make that measurement as well as we need to be confident. And so we're now looking to the next generation of experiments. Again, we're going to have two, one in the US and one in Japan. So June, the deep underground neutrino experiment will be in the US. That's the one I work on. Hyper-K is going to be in Japan. And, I've said a few times we're really good at making things. In Japan, they had the Kamiokande detector. They built another one that was the same but bigger, and they called it Super Kamiokande. And they're building another one that's the same but bigger, and they call it Hyper-Kande. But yeah, so for the rest of this talk, I'm going to tell you a little bit about June. So June will send its beam of neutrinos from Fermilab near Chicago to a mine in South Dakota called SURF, the Sanford Underground Research Facility. Fun fact, this is the mine where the solar neutrino experiment was that I showed you before. We are under construction at the moment. We're planning to turn on around the end of the decade, sort of late 2020s, early 2030s. So the far detector site is going to be in this mine in South Dakota. It's an old abandoned gold mine. You can see the top right photo. This is what it looks like from the outside. It's actually a really beautiful place called the Black Hills. Really lovely, some very good hiking around there. The yellow bit on this picture is the new area that we're going to excavate for June. And you can see there's sort of two big long caverns. Each of those is going to hold two massive neutrino detectors. Here's another way of looking at it. So it's a mile underground, 1.5 kilometers, or 4,850 feet, because they're American. They call it the 4850 level. There's already some lab space at that level, but we've been excavating new space to put June detectors. All of the rock that gets taken out for that has to be taken up the mine shaft, and then it's put in this old mining area that's sort of a big hole that you can fill up with rock. We completed the cavern excavation in 2024. So this is a photo of one of the caverns. It's a little bit hard, I think, to get a sense of scale. But if you look closely, maybe I can get my mouse. That's a person there. It's absolutely huge. There's another picture here. So this is another view. Again, if you look closely, you can see these people down here. So these are the caverns that are now ready to hold our detectors, which is a huge milestone. It's very exciting. The detectors we're going to put in them, from the outside, they look like this. They're going to be filled with liquid argon, which means they need a cryostat because argon is liquid at about -2 degrees Celsius. Each of them is going to be 66 meters long. And I don't know, you work in particle physics for long enough and numbers stop meaning things, and you're like, yeah, make the detector 66 meters. If we were going to fly from here to Chicago to look at the experiment, we would likely fly on a 7817 minor plane, which is only 57 meters long. So it's 9 meters longer than a very large plane. These are absolutely huge detectors. This is a prototype that we've made that we're running at CERN. This is a nice small prototype, which is sort of the size of a small house, but it's not as big as a plane. And what you can see here is the wire planes. That's how we're going to read the detector out. And so there's 2 wire planes you can see that have been installed. The inside of the cryostat is the sort of silver that you can see, and that's the metal that's going to sort of be able to hold the liquid argon. And the reason it's sort of corrugated is to allow it to shrink when it gets cold in liquid argon without breaking. So you can see someone here that's installing the wire planes. You can see here, you can see a little bit more detail of the wire planes. Each module contains thousands of wires that are spaced 5 millimeters apart. And we have 3 planes going at plus 60 degrees, minus 60 degrees, and vertical. And the reason we have 3 planes of wires is if you want to work out where a particle was, you need to see if it hits this wire and this wire, then you know that it's right in the middle. And the 3rd plane just gives you a little bit of redundancy in case something breaks, because it's not like we can drain the liquid argon out and go in the fix. This is another picture. So this is from the wireplane factory, which is at Daresbury Lab between Manchester and Lancaster. The UK is actually making 137 out of 150 of these wireplanes. And I can't remember how many we've made so far, but like we've made a decent start. In fact, we've started shipping them to the US. So we just did our first shipment of wireplanes to the US. This was a really stressful experience for all involved, because these are, you know, incredibly thin wires. They're 5 millimeters apart. You make it really precisely, and then you put it on a boat and hope that it doesn't get dropped somewhere. So they're sort of packaged up really specially in these containers that have temperature sensors and motion sensors and springs to try and isolate them a bit. And we've been doing some testing of, you know, shipping the sort of reject ones that we don't really think we can use, but we just make sure that we can get them there safely. Another bit of testing we've been doing is working out how we're going to get them down the run, because these planes they're sort of 1.5 by maybe 4 meters, which means they don't fit in the lift. So this is a photo from one of the original tests, where they ended up sort of strapping it up to dangle below the lift and then lowering it 1.5 kilometers down, and then you've got to get it off at the bottom and you assemble the detector. I think it's all very cool. It's really good progress. As I said, we're going to turn on around the end of the decade. This is a recent meeting of collaborators who work on June. There's actually many more people working on the experiment who aren't in this photo. We're about 1,000 people altogether, which is the biggest neutrino physics collaboration ever. It's still small compared to some of the particle collaborations at CERN. But the aim is that June is going to make the definitive measurements of neutrino oscillation with precision that we've never had access to before. And hopefully we're going to be able to answer this question about neutrinos and antineutrinos. We're also hoping to be able to answer how many neutrinos there are, how they interact with complicated nuclei, which one is heaviest and which one is lightest, as well as being able to study neutrinos for supernova if we're lucky and one happens, and being able to use it to search for new physics like dark matter. Okay, but I've been talking for about an hour. Thank you all for listening. I will leave you with, I've thrown a huge amount of information at you. The only thing is that if you remember anything, neutrinos are the most abundant matter particle in the universe. They almost never do anything, but they have been at the heart of some of the biggest mysteries of particle physics. They surprised everyone by being able to change between the different flavors. We are now asking whether neutrinos could be part of explaining why the universe exists, and I will say unclear so far, but we have experiments like June coming up in the next decade that hopefully should be able to answer it. So I will leave it there, and thank you all very much for listening.
Just very quickly, at June, why don't you simply build a bigger lift so you can move things up and down? And why not build the panels over in America? Sending specialists over there, so you don't have all that worry.
Yeah, no, both very good questions. Okay, so the second one, why don't we just build in America? We are building some in America. The other sort of 13 are being built in America. But the idea was that we would build half and half in America and the UK. And we got our factory up and running and successful a lot. And the American one had problems, so we've just taken over the one. It does then lead us to the presentation problems, but we're better at making possible. Don't say that too loud. No, we could send our specialists there, and we've done that for our Christmas. But for June, you also need the sort of infrastructure of building the factory and things like that. Why don't we build a bigger lift? I've learned a lot about lifts recently. This doesn't quite answer your question, but it's a related fun fact. The June lift is not in compliance with American safety standards lifts because it's physically impossible for it to be, because the cable is 1.5 kilometers long. And the American safety standards are that the cable should be able to hold some number of times its own weight. But it's not possible to do that because the way you make the cable stronger is by making it thicker, and that makes it heavy. And so you get caught in this sort of circular logic. So that doesn't quite answer it, but I think the answer is there's a lot more challenges about mining lifts than I thought there were. And for whatever reason, the experts that run the mine decided it's easier to dangle things off the bottom than just mine.
Thank you. So I was just wondering, is it possible to tell whether something is matter or antimatter just by looking at it? And if not, then how do you know some distant galaxy is not fully made out of antimatter?
Yeah, okay. So the question, in case you here, is can you tell whether something's matter or antimatter? And how do you know that something's matter? So in a particle detector, there's sort of two ways you can tell something's antimatter. The first is you can usually tell its charge. And so you have to do some knowledge of knowing whether, so for example, a neutrino produces an electron. An electron neutrino produces an electron. An anti-electron neutrino produces an anti-electron. So if you can tell the charge, then you can work out whether you're looking at matter or antimatter. The other way that you have to know if you're looking at antimatter is to see if they're annihilated. Because if an anti-electron travels through argon for long enough, it's going to hit an electron and it's going to annihilate against it. And that is why we know that there isn't some sort of pocket of antimatter out there. Because if there was, we would expect that at the edge where the antimatter galaxy sort of meets the normal galaxies, there would be matter-antimatter annihilation, and we would get loads of energy out of that. And what we'd expect to see, I think, if that was happening somewhere like gamma rays or X-rays or something coming there. And we don't see that, so we don't think that happens.
Okay, thank you.
So there and then there.
You talked about looking for the differences in behavior between neutrinos and antineutrinos, and you talked about particle accelerators generating neutrinos. Do those same particle accelerators generate antineutrinos as well? Yeah, okay.
Okay, I made some slides. I'll show you. Okay, so the way you make neutrinos in the particle accelerator is generally your particle accelerator, you have one that accelerates protons, and you fire those protons into a target, which is just heavy stuff. Often they're beryllium or graphite. And the point is that you want to sort of smash those protons into something to have lots of interactions, and they produce lots of secondary particles, including particles called pions and kaons. Those ones are the ones we're interested in. They decay to produce neutrinos. So you then have these things called the magnetic forms. Charged particles will curve in a magnetic field, and so you can choose the magnetic field so that the positive charged particles curve in and the negative charged particles curve out. So now you've got a beam that is only, let's say, positive pions. Positive pions decay to produce anti-muons and muon neutrinos. And then finally, you put a massive block of steel in the way that absorbs all the muons and all the electric pions and doesn't bother the neutrinos, and then at the end you've got a beam of antineutrinos. But what you can do is you can reverse the polarity of these magnetic forms so that instead you focus the negative pions, which decay to produce antineutrinos. So yeah, it's actually, we can create both.
But presumably not simultaneously. You would.
Yeah, you get a little bit, we call it wrong sign contamination. You get not too many antineutrinos in the neutrino vein, but you do get a few neutrinos in the antineutrino vein, but not too many.
Thank you.
Mostly. Okay, there was a question there. Oh, great. Okay. Okay, let's go up there and then we'll. Yeah, great question. Why do neutrinos arrive first after a supernova? So when a supernova explodes, it's an incredibly dense environment. We think about light, traveling in straight lines, all of that you know in school. From a particle physics point of view, light is particles that are called photons, and photons interact electromagnetically. And if you remember my little list of the forces, the electromagnetic force is stronger than the weak force. So if the environment is dense enough, like it is inside a supernova, the photons will actually interact with each other and with the other particles inside the supernova. And that slows them down because they're getting sort of absorbed and re-emitted again, and it just holds them up. Whereas the neutrinos only interact briefly. They don't really care that it's a very dense amount of stuff away, and so they shoot straight out. And so when it leaves the supernova, the light travels faster than the neutrinos, but the neutrinos make it out of the supernova. And the reason I put this picture up is I told you it's happened, we've seen it once. So it was this supernova 1987A. It happened in 1987. They were really optimistic and they named it A. I don't think it was the second one. But I mean, we make a really big deal of this in the neutrino community. That in the top, those are the 3 detectors that saw it, 4 neutrinos, and the number of neutrinos that saw it. So we've only ever seen 25 neutrinos. But if we could see them, there's huge amounts of stuff that we can learn because they arrive earlier. So step 1 is if we see them, we can alert the telescopes. And there's a worldwide network with SNOOS, the Supernova Early Warning System, which is all the neutrino detectors around the world are connected together. And if one or more sees a sudden increase in the number of neutrinos, you can register to get an alert. And then, the astronomers can point their telescopes in the right way and hopefully see the start of a supernova, which we've never seen. But also, the neutrinos can give us information. They can give us information basically about the environment which they were produced, which will allow us to test different models of how a supernova actually happens and learn a lot about the sort of early stages of the supernova. So we're really excited. We saw it once. We think we can learn a lot if we can see it again, and so we're really, we want to get all these detectors online and make sure that we're going to be able to see it. I think we're sort of predicted one supernova in range every 10 years. So we might not see one, but that's an average, so we might. And what everyone is living in fear about is that one will happen in the next 2 years before 20. That would be the disaster.
Hi, thank you. That was a really fun talk. My question's a bit of a two-parter. I think they're a bit related, I guess. Firstly, can I just clarify the distinction and maybe if the terms are interchangeable to some degree? I guess not. What I'm referring to is size and interference and heaviness and mass. So by the heaviness increasing to 100% between generations, are you referring to the mass, or are you referring to like the interference / size?
No, so that is mass. So when I talk about moving heavy, I mean mass. So when I say the muon is 200 times heavier than the electron, that is mass. The interaction and the size are different, and that's to do with the forces.
I see. And with each generation, do they increase in interference?
No, not necessarily. So actually they don't, because they tend to experience the forces the same. That's what sort of groups them in the sort of rows in that table. Everything in the row will experience the forces the same, and so they would all have the same sort of interaction observing, or the same cross-section size. But they would just.
I see. And sorry, the second part was about neutron oscillation. Does that phenomena of oscillation occur for the other particles, such as electrons or muons or taus, or the different quarks between the generations as well, or is this just a phenomena with the neutrinos?
Yeah, that's a great question. So it's not just neutrinos. There are actually particles called kaons, which are not fundamental particles, they're made of quarks, but we've seen oscillations in as well. I can't remember which was observed first, actually, whether it was, I think the neutrinos was observed first, but no one really understood it, and we might have understood the kaon one first. Whether electrons, muons, and taus can oscillate is a question that I like to ask PhD students in PhD fibers, because all of the theory sort of says that they should, except that they have such different masses. So all of this quantum mechanics, when I said, you've got a red ball and it eats all three of the beach balls in different amounts and they all travel, that only works because you don't know which beach ball it is. If you know which beach ball it is, then it all falls apart. And the thing is, because the charged electrons have such different masses, you can tell which one you've got, because you can tell if it's an electron or if it's 200 times heavier than that. And so they don't oscillate. But that's a very insightful question.
Thank you.
So thank you. Yes. Yeah, it's a good question. So actually, and they are, so Super K is the one that I said did that atmospheric neutrino experiment. It's also the one that took the neutrino photo of the sun. So they do both. Often the way you do it is by the direction the neutrinos came. So you sort of get that conservation of momentum. You can't see the neutrino, but it knocks stuff out, and if the stuff generally goes that way, you assume the neutrino came in this way. So for example, with the sun, you know where the sun is at any given time, and you just look at neutrinos that see in that direction. The atmospherics come from everywhere, so you can't use the directionality. But we do have theories and models of the sort of the energy that atmospheric neutrinos should have, and so you can look for ones in the right energy range that don't seem to be coming from the sun and don't seem to be coming in the direction of the particle accelerator, and then you just sort of say those are probably the atmospheric. Cool, thank you. There was one question. Oh, it's the same one. Okay, cool. Any others? Oh, there's one right up at the back. Oh, sorry. No, you go first. Yeah. Thank you.
So I have 6 questions, but I'm gonna make one. Well, it's a classic question. So I want to know, I read this article that is that they see so much because they are the highest weight according to the different based on particles that reason. So I'm thinking that's functions that we need to help the door to open. We'll find a way to find it beyond the standard model. So that would be neutrino the key tool in that particle. group find the lead particles into the neutrons?
Very possibly, yeah. So, I mean, neutrinos are the only sort of positive evidence we have so far of physics beyond the Standard Model, because neutrino oscillation is beyond the Standard Model. You can say, okay, we also have evidence of dark matter, and that's not in the Standard Model either. But we also don't know how to detect dark matter yet, so it's a little bit less practical. But neutrinos, yeah, there's a lot of, that sort of big slide of questions that I had. A lot of the answers to that would be keys to new physics beyond the Standard Model. So this idea of the seesaw mechanism is to explain why neutrinos have such light masses. There's a theory that there could be corresponding particles we haven't measured yet that we call heavy neutrinos. And they are linked together in a way that's like a seesaw. So the heavier the heavy one is, the lighter the neutrino is. It goes like this. That also only works in a regime where neutrinos are their own antiparticle, which I didn't even really talk about, but is possible for neutrinos, and it's not possible for any other particle. Because neutrinos don't have charge, so all of the other ones, one of the big things that's different between the particle and the antiparticle is the charge. The neutrinos don't have that, so it's possible they could be their own antiparticle. And then on top of that, it also basically that would create a new way of gaining their masses that doesn't involve interaction with the Higgs, which is nice in some ways because it explains why the neutrinos are so different from the other particles. They gain their mass in a completely different way. But if we could see that, it would all be beyond the Standard Model physics. There are experiments that are looking for whether neutrinos are their own antiparticle. If we see that, it's not what I work on, but it would be the biggest breakthrough, I think, of a generation. It would be really, really cool. And in my opinion, the stuff I'm doing is the sort of lowest hanging fruit. And in my opinion, once we've done that, the most exciting thing is this neutrinos are their own antiparticle, because that just opens the door to so many more beyond the Standard Model new physics stuff. So yeah, thank you.
Yes, thank you again for the talk. It was basically a follow-up on the fractional side of it. You have the sun test and the atmospheric test, but you also mentioned earlier in your talk that they are also produced within the core of the planet. So presumably, if you're looking through the planet.
Yeah, great question. It's because of the energies. So the ones in the sun are generally higher energy than the ones in the center of the Earth. We've actually only relatively recently been able to detect for the first time the neutrinos in the center of the Earth, GeO, because they're very, very low energy. The sun ones are also relatively low energy, but they are higher. But yeah, it's a good point. So if you have a detector to both, you have to assume that when the sun is on the other side of the Earth, what you're measuring is a mixture of the two. But then you can also measure the sun when it's on the right side of the Earth and sort of subtract that out and work out how many we're making. Cool. There's one here. Oh, someone's got a microphone there, and then we'll come to you. So, right. So we have seen. Let me get this the right way around. So the probability that you see electron neutrinos when you start with a muon neutrino, you're more likely to see electron neutrinos than you are to see electron antineutrinos in an anti. So we've seen slightly more electron neutrinos than we expect to see, and quite a lot fewer antineutrinos than we expect to see. And so those are sort of going in the opposite direction. And that's a hint that the oscillation goes a little bit differently for both of them. But these are relatively small numbers. We've seen a couple of hundred electron neutrinos, and we've seen tens of electron antineutrinos, which is why it's only really hints, because if you want to really say that for sure, then you need lots of neutrinos so that you have a smaller statistical uncertainty on saying that you've seen a difference. Yeah, cool, thank you. Yeah.
I assume that now there are no way, but is there theoretically opportunity to affect the oscillations of neutrons except detecting them?
Yes. So the neutrino oscillation does get affected by passing through matter. Because you know, all of atoms contain protons, neutrons, and electrons, and you can have interactions between electrons and electron neutrinos that you can't have with muon neutrinos or tau neutrinos. And I said that the neutrinos don't travel as electron neutrinos, they travel as beach balls. But that essentially, you can imagine that it produces like a drag force that affects each of the beach balls in proportion to how much glue it's got on it and how much sort of electron neutrino content it's got. And so that does affect the neutrino oscillation without detecting it. Whether you could do anything with that, I don't know. Mostly we just account for it, like we know that it's going through the Earth. I mean, I'll tell you one thing actually, there are ideas that you could use atmospheric neutrinos to see what's inside the Earth, because it could be affected by the changes between the different layers of the core. And I think we need more data, we need to get better measurements, but there are ideas that you might be able to see the transitions within the core of the Earth by looking at the oscillation of neutrinos.
Thank you.
Cool, thank you. I'll repeat it for people online. So the question was, how much sooner do neutrinos from the supernova arrive from the light? It's not a lot. I think it's minutes. Yeah, I mean, there's approximately enough time, I think, if you're ready to get the alert. I think if your telescope is slow and it's pointing the wrong way, then it's just enough time to be a bit stressed about it. Yeah. Question here?
Yes. Does the speed of the come back to
Good question. Does the speed of a neutrino from a supernova differ from the speed of a neutrino from the sun? Yes. So the speed of the neutrino is determined by the amount of energy that it has and its mass. And the supernova neutrinos tend to be different energy from the sun. And I'm not sure if it's higher or lower energy, but it's definitely different. So it probably is a different speed, but it's probably only very slightly different. I don't know if you would be able to measure it being different. Do you know what I mean? Like theoretically, yes, it's different, but I don't know if we've ever measured it.
very slightly?
Exactly, very slightly. Yeah. Good question. Oh, there's a question there behind you.
Review why the universe exists, and can you explain why?
Yeah, okay. So it's a little bit complicated actually. So I said for the universe to exist, we need to have some physics that's different from matter and antimatter. And so the short answer is, if we can see neutrino oscillations being different from neutrinos and antineutrinos, that's evidence that physics is different from matter and antimatter. The long answer involves a lot more ifs, and it actually involves what we were talking about with the seesaw mechanism. So the way this would actually work is you would, here's the ifs. Number one, if we see differences in neutrino oscillation. Also, if neutrinos are their own antiparticles, and if the seesaw mechanism is true, and you have these heavy neutrinos, and if the difference between matter and antimatter is the same for the heavy neutrinos as it is for the neutrinos we know about, then those neutrinos would be created in large amounts in the early universe, and they would decay to produce quarks, and they would decay to produce more quarks than antiquarks. And that is how you would get that imbalance in the universe. So it's actually a lot of, this is sort of step one, which is why I was very like, could they? Maybe. this is step one, but even if we prove this is true, there's still a lot more things that we have to prove before we can say that neutrinos are the reason the universe exists. That's a really good question.
Thank you for a very interesting talk. I think with particle physics, with neutrinos and with everything else, a lot of the experiments that you do use these sort of massive detectors like CERN and like June, and every time the new one seems to get sort of bigger and bigger. Are there other ways to do experiments with particles, or is it just a case of sort of every time we want to go deeper, we kind of have to increase the scale, I guess?
Yeah, I mean, it depends. I think it's fair to say you always have to increase the scale, but maybe there's different scales that you can increase. So in neutrinos, we generally go for bigger detectors because our biggest problem in neutrino experiments is getting enough neutrinos to study. And so if your detector is bigger, it's more likely a neutrino to interact. The other thing is it's more likely a neutrino will interact if it's denser. So the other way you can go is to make your detector out of a heavier material. And so June, for example, is going to be filled with liquid argon instead of water because it's a little bit denser. Argon has 40 nucleons in it, water has 20. So that's another way that you can sort of scale up. Another way you can go in particularly other areas of particle physics is having more precise detectors. So having better resolution or better measurements of energy. Or the other thing you can do, and this doesn't really apply to neutrinos, but things like CERN, is go to higher energies. So when CERN is accelerating particles and colliding them together, the thing they tend to want next is higher energy. And actually in the US, the way they think of their particle physics program is the energy frontier, which is where to do it better, you need more energy, and the intensity frontier, which is neutrinos, which is to do it better, you need more intensity. So maybe you need more intense beams of neutrinos, where there's more neutrinos in your beam, or a way to measure more neutrinos in the detector. So often it does mean bigger, but you can have really clever ways with technology that can also do things better as well. So these experiments that are looking for whether neutrinos are there and antiparticles, there's two approaches, and one of them is build something really big, and the other one is looking into like quantum sensors and really sensitive germanium detectors and things where it's quite small, but it's really, really precise and really sensitive, and so maybe you gain in that way.
Thank you very much.
Thank you. Why do we think they exist? Well, they were first detected by putting a particle detector near a nuclear power plant, and they saw. I mean, basically, maybe it's the same answer for any way that you detect it. Is that you see stuff going out of nowhere. So it's a sort of conservation of momentum thing. That you see stuff that's going that way, there must have been something that came in the frame of it. The original reason people thought neutrinos existed was also actually conservation of energy. So they looked at beta decays. Beta decay is when a proton, let me get this the right way around, a neutron turns into a proton, an electron, and an electron. Back in the day, they just thought it was neutron turns into proton and electron. That is a two-body decay, which means that you can solve it exactly. You can solve the equations and you can work out, and crucially, the electron should have the same energy every time. And so they measured the energy of the electrons, and they found that it wasn't the same energy every time, it was a system of those different things. And that was yet another crisis of physics caused by neutrinos. That was in like the 20s, maybe before that. Maybe 30, I'm not sure. But it was, I want to say 1918, but I'm not sure. But like people were proposing that conservation of energy wasn't right. It was really like people were ready to throw out all of physics. And then a guy called Wolfgang Pauli proposed, no, actually, energy is conserved. There's just a third particle that we haven't measured. And that is taking some of the energy, and that's why we don't see the same energy for the electron. He said that these particles had to be very light, electrically neutral, and impossible to detect. And at the time, he was really upset with himself because he said, "I've done a terrible thing. I've postulated a particle that cannot be detected." And he thought it was like the worst thing a theoretical physicist could do is come up with a theory that you can't test. But they did eventually. I mean, it took about 30 years. But they did in the 90s. Fun fact: they detected it using a nuclear reactor. Their original plan was to use a nuclear bomb at Los Alamos, and the idea was, we accept that nuclear bombs tend to shake your particle detector around a lot in a way that's not good. We've solved it. At the same time as the bomb goes off, we're going to drop the detector down a really big hole, so it's in free fall while the bomb is exploding, and then we'll put like cushions and stuff at the bottom to catch it. And that was approved, but sadly for everyone, before they managed to do it, someone was like, "Why don't you just use a nuclear reactor?" Which is a much more sensible idea. Okay, there's a question on here. Oh, someone's got a microphone up there, and then we'll come to you.
So thank you for the lecture. It was really interesting. I was just thinking, if there's this such great amount of neutrinos in the universe, could there be regions of space where there's a high enough density of neutrinos to sort of dominate the gravity to create almost a neutrino galaxy?
Oh, that's a good question. I mean, theoretically, I think it's possible, but I think probably not, because they're so light that you would need such a huge amount of neutrinos that it's quite unlikely. Because they're so light, the gravitational attraction between neutrinos is relatively small. But I don't think so, but it's interesting. Thanks. Question here?
Thank you so much. You've talked a lot, quite a bit about energy, neutrino energies. Where is the energy in a neutrino, and what impacts when a neutrino is, I guess, created? How much energy it has?
Good question. So the energy of a neutrino is basically the way it sort of affects the neutrino is by making the neutrino go faster. Yeah, because the neutrino has a fixed size, so the only thing you can do is make it go faster if you give it more energy. The thing that determines how much energy a neutrino has is the energy released in the radioactive decay that produced it. And that is generally a function of the nuclear physics of the radioactive decay. This is a thing that nuclear physicists who are cleverer than me can calculate, and they tell you, they call it the Q value of this is the amount of energy that's released in this particular nuclear decay. And certain nuclear decays just produce more neutrino energy. So it produces more energy in general, and some amount of that is given to the neutrino and it makes it go faster. Or, like when we make a neutrino beam particle accelerator, these particles that decay to produce the neutrinos are also traveling, so they have energy. And so then those neutrinos will have more energy because they'll sort of inherit it from the particle.
So is there a upper bound and lower bound on how fast a neutrino can move?
There's definitely an upper bound, because nothing can go faster than the speed of light. Some people might remember about 10, 15 years ago, there was a claim that neutrinos had been measured to go faster than the speed of light. It turns out that was a cable that wasn't plugged in properly. But it was in the headlines for a while. So as far as we know, they cannot go faster than the speed of light. The theoretical lower bound is 0. In practice, because they're so light, if you give them any reasonable amount of energy, they're going to shoot on. So in practice, we generally just assume neutrinos travel at the speed of light all the time, and the calculations are good.
Thank you.
Cool. Thank you.
Michio, extra dimensions is front and center in the scientific world. No longer just science fiction. I want to understand how it works in string theory, in fundamental physics, and then potentially in cosmology in large extra dimensions. So how significant is this in our understanding?
Let me tell you a story. When I was a child growing up in San Francisco area, I used to visit the Japanese tea garden and to visit the carp swimming just beneath the lily pads in a two-dimensional pond. I used to spend hours looking at them. They would swim forward, backward, left and right. Their eyes were to the side, and they couldn't see me. I was in the third dimension. I was in hyperspace. They were totally unaware that there was a universe beyond their pond. And then I thought, well, what happens if I reach down and grab one of the fish, lift the fish up? Maybe that fish was a scientist, and the scientist would say, bah, humbug, science fiction, there's no world of up. Up does not exist. Well, I would grab this scientist, lift them up in the world of up, hyperspace, the third dimension. What would he see? He would see beings breathing without water, a new law of biology. Beings moving without fins, a new law of physics. And then I would put the fish back into the pond. What kind of stories would he tell? Well, today, we physicists believe, we cannot prove it yet, but we are the fish. We spend all our life in three dimensions. We go forward, backward, left, right, up, down, thinking that anything beyond our pond, anything beyond our little puny universe is science fiction. We say, bah, humbug. We can't say that anymore because the concept of higher dimensions now is the biggest game in town. You see, in three dimensions, there's not enough room to put all the laws of physics. But when you go to this larger pond, this pond of hyperspace, then all the laws of physics just fit together like a jigsaw puzzle.
In our three dimension, the laws of physics are there, we can explain things, but there are lots of pieces that seem to be random, that you have to enter constants by hand, and so you might have 30 or so constants of physics and more in cosmology, and they look like they all have nothing to do with one another.
That's right. I like to think of a crystal. Let's say a crystal, a beautiful crystal, shatters and lands on a tabletop. And they're little insect-like flatlanders living on this tabletop. And they say, let us reassemble the crystal. Well, they bring it together, and then they have one crystal. It's called the quantum theory. Okay. They assemble other pieces of the crystal. It's called relativity, theory of space-time. But then they try to bring these two chunks together, and they cannot. No matter how they bring these chunks together, they cannot. And then one day, someone says, let us go to the world of up. Let us move one crystal up and then fit it into the third dimension, and it will create a beautiful unified crystal. That's where we are today, we think. We live in a three-dimensional world. We see pieces. We see the electromagnetic force. We see gravity. We see nuclear force, little pieces of this unified field theory. We bring them together. Now we have the theory of the quantum theory, the theory of the small, the theory of atoms. We have the theory of Einstein, the theory of space, time, relativity, but they don't fit together until you go into hyperspace, and then they fit together beautifully.
So when they fit together, what does that mean? We now learn that we need 10 or 11 dimensions, only 3 of which, or 4 if you include time, that we have, and so there are as many as 6 smaller dimensions, and what's happening in those dimensions? Why do you need 6 in string theory?
Well, today we see the world as is very broken. We see pieces of it. But at the beginning of time, when the universe was first created, that's when the crystal existed in its perfect form. We call it the superforce. A single superforce held this crystal together, but then we had the Big Bang, which shattered this crystal, giving us the shattered universe of today. When you look around you and you see the different forces, mountains, clouds, planets, it's broken. We live in a horribly broken world. But at the instant of creation, there was perfection. There was perfection in a higher dimension. This perfection cannot exist in 3 dimensions. Now, some people say, well, why 10? Why 11? Well, it turns out that there are certain magic numbers in mathematics, and numbers which have spectacular properties. It turns out that if you go to a 13-dimensional universe, a 15-dimensional universe, it's unstable. Particles would prefer to collapse down to 10 or 11 dimensions because the mathematics shows that self-consistency is important. They're unstable. Universes in 29 dimensions are simply unstable.
And so the mathematics has shown that we need 10 or 11 dimensions, including the 3 we see, to make stability. And so the simplest forces or strings can then emerge in our three-dimensional world in the particles and forces that we normally see.
That's right. So in this crystal, the crystal exists in a higher dimension, but it eventually cracked apart for reasons that we are still trying to understand. And the three-dimensional world we see today is quite broken. Now, where are these higher dimensions? Look at smoke. Smoke permeates throughout a room. Smoke permeates in all three dimensions, but smoke never disappears. Smoke never floats into the fourth dimension. Therefore, a fourth, fifth, sixth dimension has to be smaller than smoke. But atoms also don't suddenly drift away into hyperspace. Therefore, these higher dimensions have to be smaller than an atom, or else our universe would float away, okay? So we think that at the beginning of time, there was this perfection of 10 or 11 dimensional hyperspace, but these other dimensions curled up, so small that atoms cannot leak into these higher dimensions.
So these are the kinds of that look from a distance as if they're one-dimensional, but when you get very, very, very small on scales that are much, much smaller than an atom, they actually would curl around each other and be like a straw.
That's right. So that the universe we see around us really is hyperdimensional, but we can't see it because these other dimensions have curled up. They're too small to be observed.
Compactification is the word that I think string theorists use.
That's right. If I have a tabletop exists in two dimensions, but I can roll it up like in a cigarette, roll it up, and then I see this one-dimensional thing, which is actually two-dimensional if I get very close with a microscope. So we think that these higher dimensions are all around you, in your body, in your living room. The pond touches the third dimension at every point. So if I have a pond and we are the fish swimming in the pond, and you ask the fish, where is the third dimension? The answer is everywhere.
All right, now we have, that's on the microscopic scale. What about large extra dimensions that seem to be talked about now in some theories of cosmology?
Well, strings can only vibrate in 10 dimensions, but in the 90s, there was a revolution that it turns out that if you add an 11th dimension, one more dimension, then membranes can exist. Not just little strings, but beach balls and golf balls can vibrate. And perhaps our universe is a membrane, in which case perhaps some of these dimensions could be large, perhaps even infinite. So once you go from the 10-dimensional world of strings, where these dimensions are very tiny, and go to an 11 dimensions, then you're talking about a whole new picture, a picture whereby some of these dimensions could be huge. And that may even explain why gravity is so weak. Gravity is a very weak force. Perhaps gravity oozes, escapes into these higher dimensions, and that's why gravity is so weak.
The so-called hierarchy problem, which gravity may be 10 to the 39th or 10 to the 40th times smaller than the electromagnetic force. It seems that these two are fundamental forces. To have such a vast difference in scale doesn't seem to make sense.
That's right. I could put sheets of paper on the table, comb my hair, and you do this in elementary school, pick up the sheets of paper. Well, I just defied gravity. The Earth weighs 6 trillion kilograms. I defied 6 trillion kilograms with a comb by picking up pieces of paper with the electric force. That's how weak gravity is. And perhaps these higher dimensions is due to the fact that space oozes, gravity oozes into these higher dimensions.
Now these, if we look at the possibility of these large extra dimensions, which you said might be infinite in size, are we limited to these extra 6 or 7 dimensions other than the 3 we see, or might there be a vast number of infinite number of dimensions, as well as each one being infinite in size? How many infinities are we dealing with here?
Well, we think that 11 is the upper limit. Some people actually have looked at 12 dimensions. In 12 dimensions, you have 2 times. But in 13 dimensions, the universe becomes really unstable. I've looked at 13. It's a horrible dimension to work with mathematically. 12 seems to be the limit. And even in 12 dimensions, you have double times.
Yeah, I don't know what to make of that.
Right. But one thing is maybe we can experimentally see some of these objects, because if a universe is hovering just above you, it is invisible to you. Light goes underneath. And that may explain dark matter. Dark matter is invisible. It has gravity. The Hubble Space Telescope has given us maps of this invisible matter. Maybe it's nothing but an ordinary galaxy hovering just above us in another dimension. If you read H.G. Wells' famous novel, The Invisible Man, he becomes invisible because he's blown into the fourth dimension. He's hovering just above us. Light goes underneath the invisible man, but he can look down on us. So perhaps dark matter, which makes up most of the matter of the universe, is nothing but ordinary matter of a galaxy hovering in a parallel universe just above us.
Under the thinking, gravity then being the only kind of force that can transmit in some way between different dimensions. It's the one thing that different dimensions are permeable to would be gravity. Everything else can't penetrate it, but gravity can.
That's right. We are like flies on flypaper. The flypaper represents our universe. We're stuck. We can't get off. But gravity oozes between flypapers, and therefore we can actually perhaps detect experimentally the presence of alternate universes. This is not just science fiction. Perhaps with our instruments, we can detect dark matter-like objects from other universes hovering just above our universe, because gravity oozes between dimensions.
And we'll close with the aerosol tracking. So the diagram on the right-hand side shows all the NASA satellites that are actually up in orbit that are observing the Earth. And with the projection out to 2030, or at least before the current government got in there, so I suspect everything from 2025 onwards may have either been killed off or suspended. What this is modelling that was done between August the 1st and September the 14th in 2024, showing smoke, dust, sea salt and sulfates across the world. When it shows it, the smoke is from light bushfires across the world that will be shown in orange. Dust will be mauve, and you'll see on Australia there's some dust storms show up from space. Sea salt is mainly whipped up by storms and tornadoes and hurricanes and the like. And the sulfates is basically pollution and volcanoes. And you'll actually notice that over the 6 weeks of this animation that those aerosols can travel virtually around the world. There's also very little mixing between the hemispheres, and you'll see that. Note when it comes up with a map of the world, Kilauea, the volcano in Hawaii, you'll see that erupting, and you'll see the plumes of green sulfate come from there, and also Mount Etna in Italy, you'll see that erupting as well during that time. Then look to Africa and the Sahara, you'll see a lot of dust kicked up by from the Sahara and basically blown across the Atlantic towards the Caribbean area. Scary when you see the amount of burning off that was going in the Amazon and in Africa, and also the amount of the Sahara that was just moving away from the continent over the ocean. Australia was relatively unaffected. There was some dust storms there, if you were noticing it, which would have been massive to us, but compared to the rest of the world, it was absolutely tiny.
Not affected by other people's stuff.
Not very much at all.
Bit of it across the rest of Australia.
Yep, yep. All right, with that, I'll close the meeting, and hopefully we'll see you with the June meeting. Thanks for coming.